Okay, so basically what we're going to be talking about today is charge, discharge, and really just the battery's characteristics. Just to mention, if you have questions, there's a little Q&A section there. You can type your questions in there, and at the very end, I'll have some time. We'll go over any questions that you might have. So let's talk a little bit about charging to start with. So this is kind of the basic when we're talking about charging, and we're talking about our simplified 48-volt batteries. This is the basic overview of what it looks like in a controlled environment, what we might expect to see a charge curve look like. You know, pretty flat. You know, we hit it with a lot of voltage, let those amps kind of flow into the battery. So we're actually going to start when we talk about charging with current. So I've kind of got it broken up into two sections here. One as current, and the next we'll talk about charging as it relates to voltage with the batteries. So C/2 is kind of the name of the game. It's the biggest thing to consider when looking at current and charging and discharging as well. We'll get into that later, but really when we're looking at C/2, we're looking at the max charge rate of the battery. You know, if you've got a 3.8 kilowatt hour battery, that means that you can charge half of that battery's capacity per hour. So a C/2 rate. So just an FYI, we're going to be working mostly with 48 volts during this presentation. If you need the 24 volt stuff, you know, typically if we're talking about amperage, you know, just look at the spec sheet. You'll see it's a little less than double actually, but it is close. And if we're talking about voltage, obviously just cut it in half. But for the sake of the presentation, to make it go a little smoother, we're just talking about 48 volts here. So we're looking at our kind of main products, the 2.9 kilowatt hour battery and the 3.8 kilowatt hour battery. The C/2 rate, or max charge rate in amps DC, is 28 amps DC for the 2.9 and 37 amps DC for the 3.8. This number is important to factor in when you're charging, and we're going to go through some stuff here, like multiple charging sources and what that really means. You know, whether you have a generator, PV, grid, all of those different sources, making sure that you're limiting all of those correctly. You know, how PV charging works, and really we'll go into charge controllers and how to limit those. Unlike an inverter, you know, very easy to limit the output of the charge controller. So, you know, if we've got 100 amp charge controller and only 2 batteries, we definitely can always set that limit. And then we'll talk a little bit about the battery's protection limitations. So limiting the charge rate. So when it comes to charge controllers, just talking about this, you know, it's just a value that you're putting in, whether it's an amps DC, whether maybe it's the inverter's charger, which might be very similar. That might be an amps AC, or it might be in DC as well. The point being, you know, if you're trying to reach that C/2 rate, so again, let's say we have 5 of these batteries. We just take 37 times 5, and we can add that value into our charger's limit to ensure that we do not overcharge the batteries. Now, when it comes to AC coupled systems, for those that work with grid-tied PV arrays that they're adding batteries to, it's a little bit trickier. You can add the inverter's charging guidelines to say only output, let's say 37 amps, but unfortunately we find that it doesn't always work that well. So even if you do set that limit, if you're using an AC coupled system, we kind of have some guidelines. Really, it's just to stick within that C/2 related to the PV array. I actually have an entire chart I can share after this that goes through each of our access units, which are all-in-one units, and what the PV limits are when AC coupling. You might need to follow some inverter guidelines there too. A lot of these inverters like Outback, I know, and Schneider actually call out C/2 as well. The reason for that being, you know, if it's an AC coupled array, even if the charger limit's set, you know, we oftentimes see that PV goes unmitigated, and if it does go unmitigated, we might show damage to the battery. So be sure to follow those guidelines when AC coupling. When it comes to charge controllers and inverters, With the charge controller, the PV array could be oversized beyond the C/2 rate, as long as you set that limit. And as far as the inverter's charger, obviously the grid can handle, let's say it's a big charger in the inverter, again, you can always set that limit. But when AC coupling, you have to just abide by the C/2 in regards to the PV sizing. Okay. So let's talk a little bit about, let's go back. So we talked about battery protection limitations. When it comes to really anything within the battery, I'll just say this as a kind of a generalization. It's important to kind of think that the battery is, while it does have a battery management protection system, that system is not in place to prevent an improperly designed system. So if your PV is too large or you're charging too much, coming out of a charge controller all the time, then it's very likely that the battery protection will not continue to try to disconnect the battery, and eventually you will damage the battery. So it's really there as a buffer, a last stopping point, but it's not there as a end all, rely on it. Okay. So let's go into voltage now, excuse me, and how voltage relates to charging batteries. So when we're talking about charging, the majority of the charging in the lithium iron phosphate battery is happening through the the bulk. That's the main driving force. We actually recommend 54.4 volt to DC on a 48 volt battery. And it's kind of, you got to understand what a full charge means versus a resting state of charge, which is a different set. So we'll go into kind of the SOC stuff later, but it is important to know that we might charge at a higher voltage than the battery actually rests at. So if you charge a battery fully, disconnect the charger, you'd expect it to settle a few volts. As far as using float voltage, I know it's recommended. As far as kind of my rule of thumb is, if it's a DC source, you're okay to use the float voltage. If it's an AC source, I would not recommend it. So if it's an AC coupled array, if it's a grid, the generator, try not to use the float voltage. If it's a DC coupled, maybe you're off grid or you're just using a DC coupled system in a PV array, then it's okay to use the float voltage. We actually recommend 54.0 for that. Now, if you're not using float voltage, it is important to consider your rebulk voltage. So rebulk should be set a little bit higher than you might expect, and we'll go over that during the SOC stuff. But when not using float voltage, it is important to set that rebulk a little bit higher than normal. Okay, as far as inverter compatibility in regards to charging, and really charge controller compatibility too, I get this question a lot. What are the compatible inverters? You might see some of us, we have listed on the website under integration guides. If it has an integration guide built up already, that means that we know it works. If it does not, that does not mean that we do not work with them. You just might want to have to check out a few of these kind of set points, make sure that that inverter charger or that charge controller can hit, such as, the bulk, the absorb time needs to be 60 or 120 minutes. It needs to be able to get in between there or at one of those values. If it's an older model, just double check these settings, and it doesn't mean that it does not work. Even a PWM might not be a problem, but we just need to double check that it can hit these various charging parameters. And last but not least, just double check with your manufacturer of the actual charger and see if they warranty lithium ion batteries or not. Some do not. So if they do not, then we would not recommend using that charger. As far as external chargers, so something you might plug into the wall to bring the batteries online, maybe if you discharge the batteries too low. We actually have a list of approved external chargers, but not related to charge controllers or inverter chargers. And again, I'm not going to harp on it too much. The BMS shutdown and protection is there, but it is not to be relied upon. You cannot fix an improperly programmed or designed system. Okay, now let's go into charge or discharge characteristics. So again, we'll start with the discharge curve. The discharge curve of the lithium iron phosphate battery is pretty cool to look at. It's very flat compared to other battery types. There is this drop off right here, and we're going to go pretty deeply into what that is. We actually call that the knee, and it's just a heavy drop off when the battery hits a certain state of charge. Again, back to charging, you might see here, this battery was sitting, 55 volts here, a little bit lower. Once the charging stopped, it drastically dropped. That's what I meant by you might charge a lot higher, then go into your resting state of charge. Now we have a very flat discharge after that. Okay, so let's go into current and how that relates to discharging before we go into voltage. Apologies for this, looks like a little bit of a typo there. It should say phi discharging. So C/2 still applies. We talked about C/2 for charging. C/2 is also for discharging, meaning these are your limits for the 3.8 and the 2.9. So 28 amps DC for the 2.9 and 37 amps DC for the 3.8. This multiplies when you have multiple batteries. So again, if you've got 5 batteries, it's not 37 amps DC across the entire bank. It actually multiplies out. Now, when it comes to inverter outputs, this is very important that we actually size the inverter properly. So if you have, a 8,000 watt inverter, there's no way to limit that 8,000 watts. I know of one inverter that can do it, and it doesn't do it very well. And I know of some other inverters that say they can do it, but then once the grid goes down, there's no limitation on how much that inverter can output. So in order to avoid a lot of damage or issues with the battery, it's important that we actually set that sizing guideline in place while we're doing the system. So if you've got an 8,000 watt inverter, you want 16 kilowatt hours of battery. That way it matches up to the C/2 rate. As far as surge goes, a bit of a different story. So this is actually important to kind of understand. Both our 24 volts and our 48 volt batteries are set for 60 amps at 10 minutes. Now, 60 amps at 10 minutes at 51.2 volts DC, that's a lot of power. So the surge is extremely high. 60 amps DC at 10 minutes for a 25.6 volt battery is extremely low. So this number is changing right now. We're actually going to be hiring the surge capacity of our 24 volt battery, but currently it's not very high. The 48 volts definitely the way to go if you have some higher loads, even like some well pumps and things like that. Now, a little bit regarding C/2 when it comes to residential. If you're grid tied, let's say you're off grid, you definitely don't even need to possibly hit that C/2 rate. You should not be it should be able to be sized to last the entire day. And frankly, most grid tied battery backup systems are not mostly sized for 2 hours as well. So this C/2 rate, well, I get a lot of arguments, of, well, I want to put, I got this 8,000 watt inverter, and I say, well, why don't you use the 4,000 watt inverter? Well, they need 8,000 watts. Okay, well, then the battery is probably improperly sized for the customer's use as well as the C/2. So in most use cases, C/2 is really not that important on the discharge. While it's very important when it comes to charging and being able to charge fast, you very rarely are going to be sizing a battery for a 2 hour window. Some extra protection you can always use to ensure that C/2 rate is met. Inline breakers. So, here's an example of that. if you've got 3.8 kilowatt hour battery at 48 volts, you've got 2 of those. We know the max discharge is 38 amps of DC, 37.5 to be exact times 2, 75 amps of DC is the max continuous discharge of that battery. We would probably go with a 60 amp breaker in line. That would make sure that no matter what happens, that breaker was flip if the system or the loads try to pull too much from the battery bank. Some other things we can do is actually let's see if I got it here. We can actually limit the discharge using some relays and some other kind of cool functions there. It's pretty advanced stuff and can take some really hard times. Or we can always use grid or generator load support functions. Basically, these functions say, if load hits X amount of kilowatts, turn on generator. If load hits X amount of kilowatts, support from the grid. These are great in a grid outage. Obviously, generator would be the only one you could use, but definitely I wouldn't rely on these functions. I would just make sure to properly size inverter to battery for C/2. Okay. So we're going to kind of be jumping through this real quick. I think we're getting pretty close to the end, believe it or not. It's a very short presentation, this one, but there's a lot I want to talk about and see if we can get through some questions when we're wrapping this up. But I want to talk a little about the knee. So the knee is basically this little section here is what we refer to as the knee, where the battery starts to drop off extremely fast. You can kind of expect to see it around 20% SOC, and even more drastic when it hits 10% SOC. So basically, this is just how the lithium battery works. It's one of its characteristics. You'd expect to see it for the any LFP battery. What does it affect, or how does it affect the system? Well, it can oftentimes kind of ruin your low battery cutout. So low battery cutout being a function of the inverter that puts the inverter in standby when the battery hits low voltage in order to basically not turn off the entire system, and allows it to charge back up without any manual intervention. If that does not occur, the batteries might go into a hard breaker set where they actually are turned off physically. And that would require somebody to actually go ahead and flip off and on a breaker. So we want to avoid the knee in that case. And this is, I tend to get a lot of questions about this. It's kind of hard to understand unless you've seen in practice. But if you've got a heavy load, let's say maybe at C/2, and you're approaching 20% SOC, your low battery cutout is just set for the standard low battery cutout. Even let's say 48.0, you might expect to see the battery shut off before the low battery cutout function works. And now you need somebody to actually go back and reset the entire system. There's things we can do to avoid this. Avoid heavy load as it gets down to that lower SOC. Set the low battery cutout to a higher voltage like 50.2, which is actually 80% depth of discharge. Set the rebulk and the charging parameters higher, so there's more charge available more often. And we can even adjust the low battery cutout delays, or sometimes it's called the hysteresis. So we would set the low battery cutout delay to be more sensitive, so less time. That way the low battery cutout function happened before the batteries went into a state of protection. So while this mostly is not a problem in a residential system, for any systems where you might actually be utilizing that C/2, this might be an issue to keep in mind. Okay, so we'll wrap up here with some stuff about the state of charge of the battery. So on the right here is actually at C/2. So batteries being discharged at C/2 here. And this is what we would consider our voltage to state of charge correlation. 52.5 is where the engineers put it, or higher for 100%. I see it about 53. 53.3 is 100%. But from there, this is actually pretty accurate. So you'd expect about, 51.7 at 95, 51.6, 90, and so on and so on. 48.0 is actually what I would consider absolutely 0% state of charge. So how do we calculate resting state of charge? Some things to consider here: it has to no longer be in a state of charge. There has to be some sort of load on the battery. And it's important to kind of understand that the real world expectations and what you see on this graph may differ, as this is a controlled environment this was done under. Even I can see it in the field when I go out there. It often is a little bit different. It does give you kind of a general idea of where your battery's at as far as state of charge. It also helps us with battery monitoring. So if you have a battery monitor of choice, we can always help program it based on these kind of values. I've been asked so many times, what's a good battery monitor to work with? I tend to point people towards the Victron BMV. It tends to be the most accurate when it comes to lithium iron phosphate batteries. Some of those old Trimetrics and things like that don't seem to work very well with lithium iron phosphate batteries. As far as our own state of charge, currently we do not have a state of charge meter on it. We do have an added solution with the Gila Edge, the third-party solution, where you can get your batteries ordered, I believe, with the state of charge meter. I believe those are getting ready to ship now. So if you ever have a customer that's really set on seeing state of charge, you can always, look at this solution with the battery. But you can always use other battery monitors as well. If you are setting up a battery monitor, if it's a Schneider or an Outback monitor, go to our integration guides. You'll find the exact set points that we find to be the most accurate. But also be sure to give it time to calibrate. Can't tell you how many calls I get of customers saying their battery monitor is not working properly with all the settings, and they've only given it like a couple days. Sometimes it takes weeks, sometimes even longer, for the SoC to really calibrate correctly. So why would you want to know this correlation? Why would you want to know about state of charge? Really, it's going to help a lot when it comes to advanced programming based on what the customer is looking for, what they want their mode of operation to be. Knowing these values and where the battery sits, you might be able to set things like how high the rebulk is to make sure they're utilizing more PV. You might want to set it, 51.4 instead of 50.2. Make sure that battery's charging as much as it can. You might want to use these set points, these SoC readings, to set some sort of grid support or a generator to come on. Maybe your customer wants a generator to come on at 20%, then we can use that. It also helps us avoid what I was talking about earlier, the knee. If you know where that knee happens at about 50.2, then you know where to consider setting certain support functions if you are using heavy loads. It also really helps when it comes to cell voltage. If you have a grid-tied system that you're looking to sell off, we don't want to sell too much of the battery, and for most cases, we just want to sell above the battery. So if you see that your 100% resting state of charge is about 53.0, that's probably where you'd set the cell voltage, but everything above that voltage sells off nice and clean without selling too much of the battery's actual capacity. Okay. Nice and short and sweet. I just want to mention, due to some of the obviously recent events, we're going to be hosting trainings, and they're not up on the website just yet, but you'll see them coming up now every week, couple every week. So a lot of different kind of key trainings like these ones, focusing in on some smaller, ideas, talking about things like the recent 9540A, our testing for that. Some of the stuff with the SCHIP program if you're in California, some use case studies, and even bringing some installers on to talk. So we'll be doing a real big push for a lot of webinar trainings here coming up. So keep your eyes on that calendar, and you'll see a lot more start coming through. Okay. I'm going to go ahead and pop some questions open, see if anyone has anything they're looking to figure out. Can I get a copy of the presentation? Absolutely. I'll even set the recording on the website, and I'll send you a link for that as well. Just give me a little bit of time. Oh, and I forgot to mention, if anyone does need NAPCEP certified credits, this is still accredited. So go ahead and just send me an email at Troy, D as in dog, at simplifypower.com. Just say I need credits, make sure your name's in the email, and I'll write you up a certificate. If you can't, if you didn't hear that email, you can always send this to training@simplifypower.com or just respond to the follow-up email. Okay, can you explain C over 2 versus other technologies? Yeah, sure. You know, C over 2 we're looking at as really something that pretty much all lithium batteries at this point adhere to. If you're looking at maybe a lead acid world, you know, you're used to the older stuff. Typically those are rated at they were rated at C over 20, and their maximum charge and discharge was C over 5, I believe was the max I ever saw. This question is in regards to the integration guides and what we might expect to find those. So if you have to actually go to our website, under product documentation, there's a section called integration guides. And you'll be able to actually find all sorts of good stuff in there. And if you don't see an integration guide, so maybe you're looking for a specific type of inverter that's not there, you know, just reach out to us. We're happy to look through it. You know, again, it doesn't mean that necessarily just because it's not on there, that it's not actually warranted. So please, if you're looking for a specific inverter, just let us know. Okay, next question is batteries. Are they listed for UL 1973? Yes, they are. What's hysteresis? So again, that's actually it's specifically the one I know of that has that setting is the Schneider XW Plus. So instead of what's called low battery cutout delay, they call it low battery cutout hysteresis. It's basically the threshold that you can set that for. And it's measured in, I think, seconds or minutes, where it allows you to change how long the delay is before the low battery cutout function actually works on the inverter. So, you know, if it's set for 120 seconds, then the inverter will wait when the battery hits 48.0, if that's what you have it set for. It will wait 120 seconds at that voltage before it disconnects the battery. So oftentimes we want to set that lower if we are experiencing some issues where the low battery cutout function is not happening before the battery actually disconnects. Do you have a chart that adjusts those voltages by ambient temperature? I do not right now, actually. Honestly, as far as lithium batteries go, there's really not a lot of effect when it comes to voltage, or really any effect as far as temperature and the battery's performance. As long as you're within the 0 degrees Celsius to 49 degrees Celsius, you know, that's really, there's going to be very little loss and changes in the system's performance. We are looking to get some tests done, is what I'm hearing, to kind of validate that and really show the true data. But as far as compensating, there's really no need to.